In this lecture, we're going to continue our discussion of inverse functions, and we're going to start with a little bit of notation. The inverse of the function f is typically denoted by writing f with a superscript -1. And the way that we read this is we say f inverse. I know that looks like an exponent, but that's not an exponent. This does not mean the reciprocal of f. It's an unfortunate overlap in notation that we use a -1 superscript as an exponent that means a reciprocal, and also in this manner for the inverse of a function. It can be confusing, but the context will usually give it away. When you see a superscript -1 on the name of a function, that's referring to the inverse of that function. If you want to find the reciprocal of a function, you would write something like f of x all raised to the -1 power like this to avoid the confusion. This means reciprocal. This means the inverse of f. Let's remind ourselves quickly about what's special about inverse functions. Inverse functions undo one another. So if we find f inverse of f of x, that will always be x. And similarly, if we find f of f inverse of x, that will also be x. This is the same rule that we had in the previous lecture, but instead of calling the functions f and g, we're now using this new superscript notation to indicate the inverse of the function f. Another thing we talked about in the previous lecture is how the domain and range of these functions are related. The domain of f is the range of its inverse, and the range of f is the domain of the inverse. Remember that we essentially flip-flop the roles of x and y when we go from a function to its inverse, so the domain and range flip-flop as well. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. That idea of interchanging the roles of x and y leads to our next topic, which is how to discover the inverse function of a given function. Here are some steps for finding f inverse. First thing, you need to verify that the function is one-to-one. If the function you're working with isn't one-to-one, then its inverse image will not be a function. We're only interested in finding inverse functions, and so you need to verify that the function is one-to-one. Next, if there's any function notation, like f of x, I encourage you to replace it with a y. This isn't a necessary step, but I've found that most people are more comfortable juggling the algebra that we have to do after this step if we have the singleton variable y rather than the function notation. But it can be done either way. Now here's the step that goes with that domain and range flip-flop. We're going to interchange the roles of x and y. By this I mean we're literally going to write an x everywhere where we see a y, and we're going to write a y everywhere where we see an x. This gives us the inverse relation, but it's not a function of x, so we need to solve for y, get the y alone on one side. And then because this procedure kind of abuses notation, we've used y to represent f of x and its inverse. We're going to write our final answer by replacing the y with the appropriate notation, which is f inverse. Let me give you an example of this with a function whose inverse we already know. We saw this in the previous video. Let f of x equal x cubed plus 2. We're going to find the inverse function, which we denote by f, and then a superscript -1, and then the input variable x in parentheses. You read this as the inverse of f of x, or I just say f inverse of x. So what were our steps? First thing you have to do is verify that the function is one-to-one. And as I mentioned, we've already looked at this function, but you can tell this function is one-to-one because of its graph. And that graph would pass the horizontal line test. That's a one-to-one function. Now I'm going to rewrite this expression using y instead of f of x. This step isn't necessary, but it just makes the algebra a little bit cleaner. You'll see that in this next step where we interchange the roles of x and y. So I write that x equals y cubed plus 2. This is the inverse relationship. We've now flip-flopped the roles of x and y. If we did this with the function notation, it wouldn't be awful, but it would look like this. And that's just a little bit clunkier to do, and actually this shouldn't be f of x anyway, it should be f inverse of x, and because of all of that, I just tell my students to use the y notation instead. Now we solve for y to get the inverse function in terms of x. I think most of us would subtract 2 as our next step. Then we use extraction of roots, and because this is an odd index, we don't need to put a plus or minus. And we get that y equals the cube root of x minus 2. But here's the confusing thing, y can't really be equal to both of these. We've abused the notation here. When we flip-flop the roles of x and y here, we're using y in two different ways. But these are just steps to help us get to the inverse function. So to write our final answer, we're just going to use correct notation and say that this is the inverse function. F inverse of x is the cube root of x minus 2. We could verify that these are inverse functions by composing them and showing that we get x in both directions. Here's another example. Let f of x equal 1 over x minus 4. Find the inverse function. First thing you need to do is verify that this function is 1 to 1. The graph of this function would have a vertical asymptote at x equals 4. And on the left side, it would shoot down forever. On the right side, it would shoot up forever. You can see the horizontal asymptote is at y equals 0 because the degree of the numerator is smaller than the degree of the denominator. And this graph will pass the horizontal line test. This is a 1-to-1 function. Now I'm going to rewrite this as y equals 1 over x minus 4 and interchange the roles of x and y. So x equals 1 over y minus 4. This is the inverse relation, but it's not a function of x. We want to find f inverse as a function of x. So we need to solve this for y. The most common step that people would use here is to multiply both sides by the least common denominator, and there's only one denominator here. I'm not going to distribute on the left side. I'm going to leave this as x times y minus 4. On the right side, these factors cancel and we just get 1. Now I'm going to divide both sides by x. It wouldn't be wrong to distribute the x and solve that way, but this is a little bit faster. I get y minus 4 equals 1 over x, and then I add 4 to both sides and I get that y equals 1 over x plus 4. Unfortunately, I've used y to mean two different things here. Y can't be equal to both of these. Because we've kind of misused the notation here as part of our process, to make sure our final answer is clear, we're going to use the correct notation. F inverse of x is 1 over x plus 4. We're claiming that's the inverse function. Now this was a brand new example here, so let's check our answer here. We've claimed that if f of x is 1 over the binomial x minus 4, then the inverse function will be 1 over x plus 4. Let's compose these functions in both directions. This is a check. This isn't absolutely necessary. We're doing this to check to make sure that our answer is right. So if we do f of f inverse of x, that says plug the inverse function in for x in the function f. So f is this function which does 1 over its input minus 4, and our input is 1 over x plus 4. Well, those 4's would cancel and we get 1 over x, and that just means the reciprocal of 1 over x, which is x. So we get the correct answer in that direction. If we compose in the other order, f inverse of f of x, well, that says plug f of x into the function f inverse. F inverse is this function which does 1 over its input and then adds 4. And the input is the function f of x, which is 1 over x minus 4. Well, 1 over x minus 4 is the reciprocal of 1 over x minus 4, which is just x minus 4. Those 4's cancel, and we again get x. So that really is the inverse function. We've got the right answer. Let's move on to an example that's going to have a little more to think about. This says, let f of x equal the square root of x. Find f inverse of x. And this is one that you might be able to guess, but there's a hitch that you have to worry about. If I were to ask you what was the opposite or inverse of finding the square root of something, I bet you have a good guess at what it is, but we have to be careful about that guess. Let's do this formally. First thing I'm going to do is make sure that the function is 1 to 1. We know what the square root function looks like. It's that half parabola that emanates from the origin. That would pass the horizontal line test. This is a 1 to 1 function. Now I replace the function notation with a y, and I interchange the roles of x and y to get the inverse relation. And how would I solve this for y? Well, we'd square both sides, right? I'm going to square the left side and I'm going to square the right side. And I get x squared equals y. And we'll have to come back to this line in a second. But we know that that y has been used in two different ways. To write our final answer using the correct notation, we write f inverse of x equals x squared. And this was probably your guess at what the inverse function would be. But there's a problem with this. This can't be our final answer as the inverse, because the domain of this function does not match the range of this function. Remember, that was one of our rules. The domains and ranges of these functions should be flip-flopped. The domain of our inverse function is all real numbers. You can plug any number you want in for x here. But the range of our original function is just the non-negative numbers from 0 to infinity. This function doesn't output any negative outputs. Therefore, we cannot allow any negative inputs to this function. Let me write it out just to make it clear. The domain of our inverse function must match the range of the original function. The original function only has non-negative outputs. Its range goes from 0 to infinity. Therefore, the domain of our inverse function must be restricted to 0 to infinity. How do we do that? We just say that x has to be greater than or equal to 0. Because the y's in the original function must be greater than or equal to 0, the x's in our inverse function must be greater than or equal to 0. And if we were to just graph that piece of the inverse function, not the entire parabola, but just the part where x is greater than or equal to 0, that piece of the function is 1 to 1. So if you guessed that the inverse function of the square root of x was x squared, you're almost right. You just have to make sure that you put this restriction on the variable. Let me go through the logic one more time. The outputs of the original function must match the inputs of the inverse function. The original function only has non-negative outputs on the interval from 0 to infinity. Therefore, the inputs to the inverse function must also be restricted from 0 to infinity. We can't allow negative inputs into this function because the original function doesn't have any negative outputs. We also have to make sure that the domain of f matches the range of f inverse, but that comes for free. The domain of the original function was 0 to infinity. The range of the inverse function is 0 to infinity. We didn't have to worry about that. We can only plug in non-negative numbers for x in the original function. We can only get non-negative outputs when you square something. You're not going to get a negative output from squaring a real number. So this leads into the topic of finding the inverses of pieces of functions that are otherwise not 1 to 1. Let's do a similar example. Let f of x be the function 7 minus 2x squared where x is greater than or equal to 0. Find f inverse of x. Why do we have this restriction on the variable? Well, if we look at the graph of 7 minus 2x squared, we should know what that looks like. That's a parabola which has been reflected over the x-axis, stretched by a factor of 2, and then shifted up 7 units. So something like this. That is definitely not 1 to 1. But we're not looking at the entire graph. We're only looking at the piece where x is greater than or equal to 0, which is this piece on the right. This piece on the left isn't in our domain. That part of the graph is 1 to 1. And so we can find the inverse of this function with this domain restriction. Those of you headed to trigonometry will do something very similar with the trigonometric functions. None of the basic trigonometric functions pass the horizontal line test because they're periodic. They repeat themselves over and over again infinitely. So we restrict the domain of those trig functions so that we can find inverse functions. We're doing the same thing here, just with a polynomial instead of like the sine or the cosine function. So with this domain restriction, the function we're working with is 1 to 1. So now we replace the function notation with a y. We interchange the roles of x and y. And now we solve for y with the understanding that what we've just done is an abuse of notation. We're using y in two different ways. So I subtract 7 from both sides. I divide by negative 2, and I'd put the negative out front like this. And then I take the square root of both sides. And we know from algebra that when we take the square root, we're supposed to put plus or minus here. But it can't be both. That wouldn't be a function. You can't have two distinct outputs for any input in a function. So how do we know which one to choose? Well, what we're choosing here is the sign of the range of the inverse function. And going back to our rule, the range of the inverse function has to be the domain of the original function. Let me write that out here. The range of the inverse function has to match the domain of the original function. Now, we were explicitly told the domain of the original function is only non-negative inputs. X is greater than or equal to 0. Well, that means that our outputs for the inverse function have to be positive. So when we go to pick plus or minus here, we pick the positive roots because we need to make sure that these outputs are positive. So the inverse function here is the square root of the opposite of x minus 7 divided by 2. Now this has an inherent domain restriction, right? We can't have a negative number underneath the radical. In order to make sure that the number underneath the radical isn't negative, our input for x would have to be 7 or smaller. So the domain restriction here is that x has to be less than or equal to 7. Notice that that's the range of our parabola here. We don't need to write out that domain restriction though because it's inherent. We know that we can't plug in numbers that are bigger than 7 because it'll give us a negative number under the radical. So what would we do differently if the function had been restricted the other way? If we draw only the left half of that parabola like this, that's also a one-to-one function. So what would we do differently? Well, most of the steps would be exactly the same. I would replace the function notation with a y. I'd interchange x and y. I'd subtract 7 and divide by negative 2. Let me skip to this step. And now I take the square root of both sides, just like before. But again, we know that this really has two possible solutions, plus or minus. How do we know which one to choose? Well, the range of our inverse function has to match the domain of the original function. We can't let the output be positive in the inverse function because the inputs to the original function are not positive. So this time we want to pick the negation, the minus sign. So f inverse here is the negation of the square root of the opposite of x minus 7 over 2. You have to make sure that the range of the inverse function is the domain of the original function, and you also have to make sure that the domain of the inverse function is the range of the original function. But again, that kind of comes for free in this example. In order to be able to get a real number output, we need x to be 7 or smaller, which is exactly the range of the original function. Let's try one more of this type. It says let f of x equal the square of the binomial x minus 3, where x is less than or equal to 3. Find f inverse. First, is this a one-to-one function? Well, we know what this function would look like if we were to graph its entire graph. It's a parabola that's been shifted 3 units to the right of the origin, so something like that. That might be the worst parabola anybody's ever drawn, but just use your imagination. It's supposed to be a parabola. That's not one-to-one, but we're not graphing the entire thing. We're only considering inputs that are less than or equal to 3. If we take out this piece on the right, the remaining piece is one-to-one. It passes the horizontal line test. So this is a one-to-one function. I want you to go through the steps to finding the inverse function, perhaps pausing at the spot where you have to consider the domain range issue. Okay, let's see if you could at least get to that part. So you replace the f of x with a y. You interchange the roles of x and y. To get rid of this square, we take the square root. And this is where we have to take the range into account. Because all of the inputs to the original function are 3 or smaller, that means that the outputs that we get here have to be 3 or smaller. If you use a little bit of foresight, you'll see that our next step is to add 3. So if we just keep this as the principal square root of x, when we add 3 to the other side, that's going to be bigger than 3 for almost every input. That can't happen because the domain of our original function is inputs less than or equal to 3. So to make sure that the outputs of our inverse function are less than or equal to 3, we need to choose the negative option here. Then we add 3 to both sides and we get 3 minus the square root of x equals y. And because we've abused notation, we're going to replace it with the correct notation. F inverse of x is 3 minus the square root of x. How do we know that was the right choice? Like, how do we know we did this right? Well, remember how this works. If we plug a number into f and get a result, and then plug that result into f inverse, we should get right back to where we started. So let's do that. Let's plug in 1. If I plug in 1, f of 1 would be 1 minus 3 squared, which is negative 2 squared, which is 4. And now I'm going to plug 4 into the inverse function. That should get me back to where I started. So that's 3 minus the square root of 4, which is 3 minus 2, which is 1. And yeah, we're right back to where we started. What if we had selected the plus option here instead of the minus? What if we hadn't put the negative in front like we're supposed to? When we plug 1 in here, we still get 4, But now when I add here instead of subtracting, I would get 5, which is not in the domain of the original function. We don't get back to where we started. And why is that? It's because we didn't choose the right square root. We needed to choose the negative option, not the positive option, in order to get back to where we started. We only get the right answer, we only get that reversal of the steps and get back to where we started if we choose the correct radical. That's why it's important that we make sure that those domains and ranges match. Otherwise, you don't get that reversal that you're looking for. I know your inclination is going to be to focus on these trickier examples that we ended with. And again, if you're headed towards trigonometry, they are worth your time so that you'll understand inverse functions from a trigonometric sense later. But make sure you look at some of the simpler examples too. Practice some of these problems where you've got simpler functions as well. Don't just look at the difficult ones. If you have questions about any of these examples or any examples that you're trying on your own, please don't be afraid to reach out to me. You can see me in an office hour or you can send me some emails.